So, hello everyone. So, I was asked to do a presentation on specific elements of the TaviCat platform, and I think the most important but really under the hood feature is really how we make draws in British Parliamentary. So I think that this will be more of a mid-level presentation in that I won't go into how the algorithms the code itself or but I will explain how in the general case how the draws are being decided and created. Now this will be our agenda. So first of all, I'll be going through what is the main steps of the process, and especially with team positions, making sure that everyone is in these different positions the same amount of time, how pull-ups are decided, and how we put all of that together to create the optimal pairings for a round. Assuming we have time, and we will, I also have a couple bonus points for you all. So first of all, how elimination brackets are created, and secondly, how round robin tournaments are run using TaviCat and the mathematical intuition behind it. So without further ado, I'm Etienne Bollet, a developer of TaviCat, and let's begin. So, in brief, computers like numbers. They can't be like this team looks better, they want to know that they can only know this team has this number of points, has been in position OG once, OO once, CG 0 times, and CO twice. Something like stuff like that. So computers just need to have the numbers behind the pairings. And with those numbers, we can decide or determine how what's the best position for them, where in what bracket they should be, and if they aren't in that bracket, how bad would it be? And secondly, how bad would the pairings be if they were allocated wrongly? So what we do is we treat a draw as an assignment problem. And in more the graph theory terms, we want a bipartite graph between teams and positions, but really what it just means is we want to give each team and we want to assign each team to a specific debate and side. So then we can draw lines between where each team will go, and there will be no position left unfilled. And here we want to avoid teams going between different brackets other than for pull-ups. Thankfully, I did not have to program this. I found someone else's code and I put it in. But I did study it in some university classes, but what we use is called the Hungarian algorithm. So what it does is that it does the assignment problem. It solves it for us in any case where it tries to find, we say, how bad would it be if a team were in such position, such debate and side, and then we'll try to minimize it between the entire round. So the main thing is that teams should be assigned each side an equal number of times. So we don't want teams to be always in OG and another team that's always in OO. We want all the teams to be in each side roughly an equal number of times. And so, however, if there are a number of rounds that is not divisible by 4, then we know that it's impossible for them to always be equal. If there's a tournament with only 3 rounds, each team in the optimal case, would only debate in three distinct sides, like they might have never done CG. However, the main there are it's a bit hard to like quantify like how bad what's the imbalance the between the sides that a team has done. Like, would we want to prioritize like well, that'll be later, but what we have is like three different ways that we've implemented, and each has their particularities. We have the simple way, the population variance, and the Rene entropy. And then when we get that measure, we can also like we can also modify it by changing like the exponent we put on that cost. So there aren't any formulae on this slide, but it does explain each uh, what what each method entails. So the simple one is just the number of times a team has been in a position. So it does the calculation 4 times, once for each side, and then it finds what side they have debated the least and subtracts that. So if a team has been in OG 5 times and the minimum was over, they have done no times, the then the simple formula would say, okay, so there'll be a penalty of 5 if they're reassigned to OG. Population variance is more of a statistical measure where it's like using the standard deviation in the speaker or team tab, but it's going between like we have 4 populations, and those 4 populations are the number of times they've been in on each side, and then we try find like the variance if we assign the team to a specific side. So if we were to allocate that same team to OG again, then we have like 5, 0, and then some other numbers. So then we can say, okay, the variation is quite high if we put them there, and the variation would be reduced if we put them in OO. These two are just a couple options. What we also have is the Rene entropy, and that's the default that we have. So this was like a big like revelation to me, and it was because it goes into like what we think of as like information entropy. So let's say you have a coin and you flip it. How much information do you get by flipping that coin? If it's like fine-tuned, if it's like non-biased, then you know that you have one side 50% of the time and the other side another 50% of the time. And so we call that like a bit of entropy, of Shannon entropy to be precise. Now, how can this be applied to debate? We can see, so what we want is like to have it equalize. So like if you were to flip a 4-sided die, you would want them to be you'd expect them to be in the same in different positions, like 25%, 25%, 25%, 25%. And so what we're trying to do is we're trying to make that calculation always that 25% chance. So it measures the diversity of the positions. Uh, And the nice thing with the Rene entropy is that it is more generalizable, and we can like fine tune it. So I have the example here where you have 0 as, so let's say you have 2 teams, And first number is the number of time they've been in opening government, opening opposition, closing government, closing op. And what do you want to, and then we can like decide whether this one is more in balance or this one, where you see that there's like equilibrium between these three, but then there's like this this which is lower, or here where like 1 1 1 and then 5. And if we were to change, if we were to like fine tune it, we can go say we prefer something like this rather than something like this. By and the cool thing is, so with and I think that is why we chose to go with Rennie by default. Really, I kind of prefer this one to this one, where you can see that the numbers are closer together, even if like they have never done opening government rather than this one, but it depends on the tournament. And next we have like the exponents. So not only do we have like the fine tuning of the Rennie order. Wait, I think the default of the Rennie order is like 2 in Tabby Cat, but then you can put it to 1, which is the Shannon entropy. And I think it's really cool to just play around with this algorithm. But not only do we have that, but we also have like exponents. So we put the exponent on like the result we get from the algorithm. And then with that exponent we can like decide like we can like fine tune a bit more to be like how bad is such an imbalance. Like if the imbalance is of 5, how bad is it compared to a imbalance of 2, or so on. Now what we have is like by default we have just an exponent of 1, so like an imbalance of 4 is twice as bad as an exponent. So an imbalance of 4 is 2 times as bad as a imbalance of 2. However, like, and this would prevent like the second situation here where you have like one that is much higher than the others. So if we were to have just an exponent of 1, then it'd be like, yeah, the 5 is 5 times worse. But then if you like put the exponent to be like 2, it'll be like, oh yeah, so it's 25 times as bad. And what this does is that it prevents like worse situations happening, because like the smallest change will make the biggest impact. But then we can also set it a bit lower. So like here I put 0.5 as the exponent, so square root. And what it does is that it kind of like levels itself off, even though it still increases. So like if you had the 1115, then it'll say that the penalty would be like 2 point something rather than like 5 or 2 point something times worse than other positions, rather than saying it's 5 times or 25 times as worse. And so what it does is that it will try to balance, but like it won't really care if like teams have like really different has like bigger imbalances, just wants to keep everything equal. Yes. So, and now we get to pull-ups, and what we do here is like less mathematical. You can see there's less content here, but what we do is we just say, okay, we have So number of teams in the upper bracket, would we be able to like put them all in a certain number of debates? And if not, we will add all the teams from the bracket below, and then we'll do the same thing with the lower brackets just to make sure that there's teams for all brackets. So this doesn't require like much specialized math or anything. Now for the Hungarian algorithm, this one is fun and appears like really often, and I'm currently trying to make like a sort of a variant on it, but for two team debate formats. So I'm excited for that. Now we use the Hungarian algorithm, which is also called Monkrez, to like match the teams between like the debates and then the sides, where we say the debates have like their bracket, and then inside the debate we have like 4 positions each. And it is quite fast, and it makes sure that it's like optimal. Now, our predecessors like Tavi 2, what they didn't use the Hungarian algorithm. What they did was called simulated annealing, which means that they tried like a whole bunch of like they made a random or like semi-random draw between the within the brackets, and then they try to see if we make this change, will it be better or worse? Now that if you just continue making like random changes, like eventually you get something like passable, but this is like more precise. But also the complexity isn't really that bad. So even if it's like 400 teams, then it's still like quite fast to calculate it all. And this gives us the guarantee that we get the least bad pairings between the entire draw. So what? So I will show an example of this in a couple slides, but I will be showing you like a square matrix where we put like all the teams. So each team has a row, so we'll put like the teams on the in the first column, and then the debates and sides on the top, and then inside the table you'll have like all the different numbers that signify like what are the penalties of like putting them in such a position. Now we because our algorithm just goes like row by row, column by column, we wouldn't want the teams to be like sorted by like their speaker scores after their brackets. So what we do is within all brackets we will like randomize them just to make sure there's no like bias. And the values inside are like the position costs that we've talked about previously. Okay. So what so this is the example matrix. So you can see that we're like on round 4. So there are like four brackets, and teams can, and we have like a good 16 teams who can, so like even if there are like 3 rounds, there's no team on 9 points, so we start with 8, and then we see okay, so the so we see that there are not enough teams on 8 points, so we'll have to pull up like at least 3. So and we can see that the numbers in blue mean that we've assigned like team B to 00 in the top room. And if we calculate that a team is not eligible for a certain bracket, we'll just put like infinity, or as my optimization classes said, big M, so that they can be allocated to that debate. And that should simplify the Hungarian algorithm a bit as well. Now you have these 3 teams, but 2 teams on 7, but we see you need to put up even more teams. So eventually, so now we'll just go take these 6s, and what we see here is that, oh, so the OO here was already taken by B, and OO here has already been taken by G, so we'll have to give them, we will have to like add 16 to like our global penalty count, but we'll have to allocate D to OG even though they have been there for a previous round. And here we see, oh yeah, we have these three teams that we have added, and then we can put them in either the top or the second room. And here, so you can see that we have like 1, 2, 3, 4, 5 teams here, but we know that one of them will have to be in the top room, so we are good here and we can just continue on. Yeah. So this is quite a few numbers, but I hope this explains well. Like we would want to minimize we will add like all the penalties and then make sure that it's like the minimum that's possible. Yeah. So now for some bonus material. So elimination brackets. So elimination brackets are done using like a folding algorithm. So there are like many different like alternatives that are done in other formats of debate, like sliding or being like adjacent, where like, oh, okay, top room would be like 1, 2, 3, 4 top 1, 2, 3, 4 teams, or in like a sliding thing, you'd say, oh, you have 16 teams, we'll separate into like 4 groups, so like 1, 2, 3, 4, 5, 6, 7, 8, and 9, 10, 11, 12, 13, 14, 15, 16, and just put top 1, second, and third, which is also, which isn't but the thing we have with folding is just that it's better competitively, and that's why we use it, where it's like we fold it instead of like ripping off a quarter and putting it up and then ripping another, we fold the brackets together. And so for like if we have 16 teams, so is the quarterfinals, we do 1, 8, 9, 16 in one debate, 2, 7, 10, 15 in the other, 3, 6, 11, 14 in the third, and 4, 5, 12, 13 in the fourth debate of that quarterfinals. Now we give like a room rank to each debate in elimination rounds. So like this one would be like room rank 1, room rank 2, room rank 3, room rank 4. And however, like maybe there's like a upset that, okay, 1 and 8 get eliminated from the room with rank 1. Now the rank of this room remains 1, and it will be counted as room 1 for the subsequent rounds, where, okay, so let's say 9, 16, 2, 7, 3, 6, and 4, 5 win. then you would have like 9-16 versus 4 and 5 in room rank 1, and then the winners of these two in the second in room rank 2. So and like that you can keep like the brackets looking sharp. However, Heavycat does not do like position balance, nor and pull-ups don't really apply in the elimination rounds. So we just like give random size and ask them to like allocate manually or just confirm the sides, which is what most people just do. Now, like big tournaments or even some small ones want to have like, as you can see, like quarterfinals here with like any elimination round seems that you'd have to have a power of 2. So like 4, 8, 16, 32, 64 teams in a break. However, what we can do is we can actually like do what's called a partial elimination round. So what we do is like we have 48 teams. So then we will only assign the bottom 32 teams to debate for the first elimination round, and then we'll just give, and then the top 16, so the third of the break, will only join in the second round. And there we have we keep like the room ranks the same, but then we will add the top teams in the second. And this is good if you to like balance the numbers of breaking teams. Okay, and now this is something that's sort of newer that so this is not something that's actually like implemented in Tabbycat, but which is like on my radar, and I've done a little bit of studying behind like how round robins work in a 14 format. So like when what I had done for like other round robins is that I had pre-calculated like all the draws, given each team a number, and then just assigning with that each team having a number from like 1 to 16, putting them in like the rooms using a quick little script that already pre-calculated and everything. However, it is nice to like understand how those numbers are like generated. Now, there are a couple like constraints. The first thing is that all teams should meet once and only once, and also that position balance still matters. So you'd want to have like so you don't want like a team to always be in like OG or any or like a specific position. So with these two constraints, we normally only have like 16 teams or 28 teams where like we can meet like both of these constraints. Okay. And secondly, what the mathematics behind it is called a Steiner-4 system. So what we do is we like give each team like a point, and then we say, okay, so what's and then we can put a line through them, be like, okay, so this line has 3 points, and then we can say, oh, okay, so this point has like 3 points, the 3 lines going through it, so this would be a debate, this would be a debate, and this would be a debate. And even if this is just 3, like an example, but you can add like extra points to be like, okay, we have a fourth point here, and then. But what you see that each point has like three lines going through it, going through them. So then you can say, okay, so they will be meeting everyone once. And so this is I find this like super cool as a visualization of like exactly what calculations we are doing. Not like we do points and then we try to connect the points so that every point is attached by a line to another to like a set of three other points so that each point has meets like everyone only once. Okay. This example is actually called the Faro plane, so it's like if you only had three teams in a debate, sort of. And with that, I say gracias. See everyone in Panama, and don't hesitate to contact me if you have any questions. Thank you.